Alright, in the previous video, we were looking at the role that Ptolemy played and the tweaks that he made had on the prevailing model of the day. And one of the trickiest bits was that retrograde motion, and that's the apparent forward or backward, well, really retrograde is the apparent backward motion of the planets compared to the stars. Sometimes, though, they do go faster forward than the stars. So there were very quirky things going on with the orbits. And one of the major tools that Ptolemy used were epicycles. And he used the 5 major epicycles, and then he used some other ones, minor epicycles. And here's an example of an epicycle, where you have a circle, so the planet is orbiting on the epicycle, which rotates around the deferent, that's the central point, and the deferent actually would orbit around the planet Earth. And so I have another little picture that I'm going to be using. So I'll show you that. So we're going to pretend that this is the Earth and Mars, and I think he used more than 2 epicycles for Mars. Mars was pretty tricky. But this is the basic idea, that you have epicycle and maybe another epicycle, maybe another one if necessary. And Mars would be rotating around this epicycle. So Mars might be doing this. And this epicycle might be doing that, and the whole thing orbits this way, let's say. So you have a fairly complicated set of motions. Sometimes it's jerking forward very quickly, sometimes it's zooming backwards, sometimes it's pretty much just doing the same thing that the stars are doing, rotating normally around the Earth. So this was a basic idea. Now some of you might be thinking, well, doesn't this mean that Mars sometimes gets really close to the Earth and sometimes it's really far away? Absolutely. If you look at Mars, if you study Mars, and you can do this on the Stellarium program, if you look at the magnitude that Mars has, or, well, actually that's probably the best way to tell. If you look at the magnitude of Mars, and magnitude means the brightness, the magnitude of Mars becomes more and more negative, which might seem like that's a bad thing. That actually means that it's brighter in the sky. So as Mars becomes more negative in magnitude, it's actually getting brighter. When it becomes more positive, it's becoming less bright. And so the ancients would have noticed this and realized this, and figured that this actually coincides pretty well with getting further away and getting closer. Did they match it up perfectly? No. But the epicycles were one way that they could actually do that. So in addition to matching the position of Mars pretty well, it also matched, they could also use it to try to match the brightness of Mars. However, even adding a couple of epicycles didn't quite do the trick. There was more going on, apparently, than what could be handled with epicycles. So there were a couple of things that Ptolemy did in addition to the epicycles. One of the things that he did was the Earth. Please understand, the Earth had to be in the center of the universe, so there was no getting around that. So if we make a little circle here, well, I'll actually, yeah, I can't use the exact picture, but I'll copy it into Paint. Okay, so now that I have this copied into Paint, there's a couple things that we can look at here. The first thing that Ptolemy did, after the epicycles, and he realized that those didn't quite work, is he took the Earth and he kept that in the center, but he moved the orbit of the first deferent off-center. So if you can imagine, the Earth might still be in the center of the universe, but you might have different circles that orbited around different points. So for instance, you could have one that was maybe bigger or smaller than Mars. There were some certainly smaller than Mars. So you could have them kind of like that. Whoops. Whoa. That got completely out of control. I do not know what's happening here with the circle. Let's try that again. So we could make a circle. And maybe it looks more like that. Very small circle. But you can see it's off-centered. That doesn't mean that the Earth isn't in the center of the universe. It just means that it's not in the center of the orbit. And this was sort of tolerated because we didn't put anything else for it to orbit around. It's just that there was a center point for the orbit, and the Earth was slightly off-center. Nothing else was close to the center, so we still considered it to be orbiting around the Earth, just not quite. And what this would do, if it's orbiting slightly off-center from the Earth, is you could have this thing going around, and it's going to spend more time. If you can imagine that you're standing right here, let's say. So this is you right here. That's a really bad person who's using the wrong tool. But what that means is that when you're looking around, your horizon is like this. And so you're seeing this planet, let's say it's Mars, this particular planet, for a very long period of time, right? Because even though it's moving through 180 degrees from your perspective, it's moving through more than 180 degrees of its orbit. So this would result in maybe, 2/3 of the orbit being spent on this side, being spent above the horizon, and only 1/3 below the horizon. And they could do this without having to do anything weird with the speeds. The epicycles would change it slightly, maybe make it a little bit longer, maybe make it a little bit shorter in terms of its time on this side. If it whips it forward at the right moment or swings it back at the right moment, you can get a couple more days or even weeks, depending on which planet it is. But it doesn't have a huge change on the time frame involved. This does, because we go from going through 180 degrees of the circle, which would be from here to here, to going through maybe 200 degrees or 220 degrees, depending on exactly how far off center we've put the Earth. So that's one thing that he did. He put the Earth off center. And then the next thing he did, which was even stranger in many ways, by the way, that was called an eccentric. It's when you put the Earth off center from the orbit, or you shift the orbit off of being centered on the Earth. The other thing that he did was he introduced an equant. And he said, and this was very strange, he said that even though the planet, so to speak, is going around this central point, it's going around this at the same rate at all times. The equant was on the other side of the central point, as the Earth is over here. So if this was a certain distance here, it'd be the same distance from the center to the equant. It's equidistant from the center as the Earth. And what that means is that if you look at, let's say, from here to here, for instance, and we'll do the same thing, oops, right there, and I'll do one that's a little bit further away. Actually, I'll do one closer, so from here to here. Now, one of the things that comes up, or that we should realize, is that if these are the same angles, this angle right here, the same as this angle right here, what he's suggesting is that it travels through this angle, the planet travels through this angle, compared to the equant, in the same amount of time that it travels through this angle, compared to the equant. The result being that here, it's moving relatively slowly. This angle doesn't have much time to spread out, right? So we only travel this fairly small distance. If you look at it on the other side, from here, and then the same angle, oops, not quite sure what happened there. The same angle down to about here, a little bit off, but you can see that it's traveling through a much greater distance. And this accounts in part for the varying speeds also of the planets. What he was saying, and I'll repeat this because it's a little bit strange, is he's saying that the planet orbits its angular motion, so to speak, around the equant is uniform. What that means is that from our perspective on Earth, it's going much faster over here when it's close to the Earth than when it's over here far away from the Earth. And he did this. One thing that he didn't want to do was make it seem like it was just randomly moving at different speeds. He wanted a nice mathematical uniformity. And he couldn't get it to move in a constant speed around the circle. So what he did instead was he said, well, let's look at angular speeds. Let's look at how rapidly it moves through different angles. If it was moving at a constant speed about the center of the circle, then its angular speed would also be constant. what he wanted, though, was for it not to move at a constant speed about the center about the circle. He wanted it to move faster at some parts, slower in other parts. So what he did was he said there's a point, an imaginary point, about which its angular speed is the same. And if we cleverly position the Earth off to one side of the center of the orbit, and something which we'll call the equant, an equidistance away on the other side of the center of the circle, if we cleverly position all of these things, with the help of our epicycles, we can get a very close representation to what really happens. Now, is this absurdly complicated? Absolutely. This is one of the knocks on this particular system, is that it is pretty complicated. However, once you get it down, once you have developed the system, it's very flexible, because if you notice that your data is a little bit off from the predictions, then you can just change the model by making the epicycle a little bit smaller, or making it a little bit larger, or adding another epicycle, or changing the position of the Earth in equant compared to the center by a little bit, one way or the other way. And so you have really almost infinite flexibility in the system to make it so that it works for whatever the data might say.